So far, we have focused on processing the data contained in a memory dump. So initially, we did this in Notebook 3 by parsing the output of volatility plugins, and then we relaxed this in Notebook 4 by working with the string contents directly, and we showed how to create UI elements that helps us investigate the textual contents of a memory dump. So now we will take a step back from the actual memory dump and instead focus on how we can use Marimo's features to build a custom environment for developing Yara rules. So we will reuse, all the reactive execution models, the ability to create custom widgets, the ability to integrate with PyTest to create a self-contained environment. Now the motivation for this is you can use Yara rules directly with volatility. So it has a plugin that runs the Yara rules for each VAD, for instance. But you can also use this same approach if you want to create Yara rules for a PE file. Now, to relate this to our ongoing investigation, in the strings notebook, we saw that there were several strings present in one of these suspicious VADs that looks like it could be related to a keylogger. So here you can see some of the strings. So this typically how this works is that when the user hits delete, the attacker has a log that records this. So it's able to reconstruct all your keystrokes basically. So this is a good candidate for a Yara rule. It's something that's easy to understand while also being fairly effective and having a low false positive rate. So to get started, let's just import the Yara package, and then so we just created two very simple rules here. Keylogger special key A, which looks for these two strings within a memory dump or a file. And then we have just a variation of this to just demonstrate how it works if you have multiple same sort of Yara rule file. So basically you just define these inline in your environment. And then we have this VAD file, which we've previously dumped to a disk. So we read this into memory. And this is basically how it works to explain what the YaraX package gives you. So like you compile this set of rules, and then you can apply it to a binary by using the scan method for using the compile rule object. And then you can iterate through all the matching rules. Like you can have hundreds of different rules, and you will be able to see it matched this rule and then this condition at this at this offset, and it has this length and so on. So that is sort of the information that's available and that we need to build our environment. What we want to build now is a way to display the matches of a rule set. So as we're developing a rule and refining it, we want to see what part of a binary is it triggering on. So here we show a representation where we have a rule set and we have a binary, and then we evaluate the rules on the binary, and then for each of the matches we have an entry here that says that okay, so this rule and this pattern within the rule matches this offset and this matched length within the binary, and then we have included the bytes that is actually matching, which is this highlighted section, and some additional context. So 8 bytes before and 8 bytes after, and then we have the ASCII representation of the same byte sequence basically. So in practice, this means that we have an ability to see exactly what part of a binary is matching. So this is super useful as we are refining our rules. So now let's focus on how to actually achieve this. So in the previous section, we had this search interface where we had an input element where you input basically your search query, and then any occurrence in the string dump that we extracted from memory, that search query or pattern was highlighted basically. This is the same approach we will take with our Yara highlighting component. So again, as always, what we want to do is create reusable functionality, and to do so we have here created a Yara scan with context function, which takes as the first argument the binary that we want to evaluate the rules on. Then we have our rule text, which is actually potentially multiple rules, and then we have a context argument, which is just the number of bytes before and after a potential match that we want to include in our representation. And then we pass in a highlight function, render highlight. So if the highlight function is not passed in, then the default is just to return the byte sequence that match as is. So again, we're just using the YaraX API here by compiling the rules and then scanning the binary data that we supplied it. And then we're just iterating through all the rules that matched and all the conditions or patterns within each match basically. And then we're extracting the offset of the match and the length of the match, and then we're doing some computations to extract the position that we want to start highlighting and then the position that we want to end the highlighting for. So there's some math here you can look at just to make sure this works out if it's at the beginning of the binary or at the end of the binary, since we have this context window that we want to include. So there's no negative indices or something like that. And then, as we iterate through all these matching rules and patterns, we just append this to a list. So we have this dictionary representation here. We have, as we saw in the table, we have the rule, we have the pattern, the condition, and basically, and the offset of the match and the length of the match. And then we have a bytes element, which is calling this function you supply. And the function render highlight takes as the first argument the chunk and the start that we want to highlight, and then the end position of what we want to highlight, and then if it's hexadecimal representation or ASCII representation that we want to create. So that is something like we need to provide that implementation basically. So now we're just including some utility functions that make it so that we can handle ASCII and hex representation in the same function, and making sure that the math comes out correctly and that we're correctly converting to ASCII representation. So you can read through this code. What you need to implement to make this work is this create highlight HTML function. So what this does, it takes what comes before, so these bytes before the match itself, and then you have the section that you want to highlight, and then whatever comes after the section you want to highlight. And this could be like 8 characters, and this could be 8 characters, and then there's some edge conditions depending if you're at beginning or end of the binary. So that's just what all this other stuff is takes care of, and there's some special math to just make everything correct, since for hexadecimal representation we need like 2 characters in the output. So we just need the mathematics here to come out correctly. Since we have provided the scaffolding, what you need to implement is this create highlight HTML function that takes the arguments that I explained above and returns a Marimo HTML object. So here you can see a template version of this, and this is what you need to work with basically. So I've just copied in our version of this, which is just relying on using the mark HTML tag, which we also use for string highlighting, and then I'm using some colors and some padding and some different fonts, and I'm styling the whole section a bit differently using a span element. Yeah, so I've included it in here again, and then you can see what happens here if I rerun Yara scan with context, again passing in the binary that we want to run the rules on, the rule text itself, and then supplying our custom function. So this one, which invokes this function under the hood basically. And again, a context window of 8. And then you can see here that Marimo is returning this nice JSON representation where we have, again, the same field as before, but now the bytes and ASCII fields are actually these HTML elements. So that's by default rendered as HTML in Marimo. So now we can just pass this list of these dictionaries straight through the table function. So this means that we get this representation back, which we showed you initially. So we are pausing in a list of dictionaries where there's a bytes and ASCII key, which already has the HTML inside it, right? So we have a way to display the yara matches as we develop the rule and refine it. Now we need the rule editor element itself. So thankfully, Marimo comes with a code editor element predefined, so we can just use that. So you can see here that the editor takes a value argument, which is the default contents of the editor, and then you have some additional arguments like the minimum height and so, like a label here for the editor, and then you can also specify the language. Unfortunately, there's no support for yara highlighting included, but that doesn't really matter much. So now we want to combine these UI elements to create a small interactive Yara rule development environment. So what we have in mind is on the left-hand side, we want the editor element, and then we want it connected to the element that shows, it highlights all the matches for the rules on the left-hand side. So there's a little bit of nuance to this. Like as you are writing the rule, it will not be valid Yara rule. So it will throw an exception, which will kill your entire display. And that will also remove the code editor. So you can't really recover from this. So a quick hack here is to wrap the scan function. So when you invoke the scan function in a try except, so you can catch the errors and just display instead of the, your highlighting display, you can say something like invalid error, invalid rule, sorry. There is something here more sophisticated you can use if you don't want it to be 100% interactive. So this will actually work in the way that as you type, the rules will automatically be evaluated on the binary, but you can also use the run button and stop functionality that we showed for the more computational intensive cells in the string section. You can also look into using state, but that's a much more advanced concept. So Marimo comes with built-in PyTest integration. So if you go to user settings like this, you can see under the runtime settings that if you enable auto run unit tests, any cell that has only test functions, meaning functions whose names start with test underscore and then something, or classes starting whose names start with test underscore something, those will be treated as PyTests basically. So what happens then is that Marimo will invoke PyTest on the command line using those cells as unit tests basically. So let's just see how this works. So here we have a basic function definition. My function, it returns 5. And then we have one of these functions starting with test underscore. So you can see what happens is that Marimo detects, hey, this is this can be used as a PyTest test basically. You have an assertion that says, okay, my function, is it equal to 1? And what we want to do is make this test pass basically. So something is wrong here. PyTest is being executed, and the output from PyTest is shown here as output. We have one test detected, it fails basically. So, again, if we change this, so remember, we have the reactive execution mode. So if I change this, Marimo will automatically re-execute PyTest using this function definition as a test, and then you can see now it has detected, still one test, but it passed. If I change this back to, let's say, 3, it fails again. So the takeaway here is that this allows us again to just keep everything in line inside the notebook. Everything is self-contained, which is really handy. And now we want to exploit this functionality to create a self-contained testing environment for our Yara rules. So the idea here is to provide a set of samples to the environment as we test the rule, right? So we have included binaries for which the rule should trigger, and then we have another samples that have nothing to do with the rule, that the rules will say that this isn't relevant at all, and there's a variation of this. It could be rules that we evaluate on a larger set of samples, and the false positive rate should be less than some certain percentage or something to make things more manageable. And these are conditions that we can specify as these inline PyTest criteria, basically. So let's just see how we could do this in the most basic way possible. So here we have a list of samples. So this one is just reading the VAD that we dumped, and then we're saying, hey, this is a true positive, and it should match these rules. It should match both rules that we have defined above, and then we have another one which is just the data is just a string, and that should match nothing. It doesn't include any of the backspace or insert or delete or home strings that we were looking for. And then we have this one. This should match only this one. And then we have this rule, which should match special key B, so because it just includes home and delete, and then you have another one which should match both rules, and so on and so on. Let's see how this works out in practice. Let's just start by compiling the Yara rule string as before, and then we have this really suite of tests. So we're using this decorator basically to create for each element here in the samples a separate test, so we don't actually get one large test, we get multiple ones. That's the purpose of this decorator function. So it loops through all the samples, and then it sets the ID of the test based on the name key of the dictionary, and then then we have the logic of the tests, which takes in the sample and these compiled rules. Basically, it evaluates the rules on the sample, the data, so this one here, and then we look at what's expected. It should be, if it should match this one, it should match nothing, and so on. Then we can do some we can just match if what we expected is what actually happens. And then you can see here that it's actually running all our it's running a test for all of our samples. And if we actually go back here and let's say we are removing this, like so, you can see like everything was re-executed again. Like it's the reactive execution model that makes this happen. And you can see, hey, this test failed using this sample data because it was expected that there were no matches, but this sample, it matched this rule basically. So something is off here. Let me fix this again, and then as I execute that cell again, everything is reevaluated, and all the tests passed. So we're not going to go into details of PyTest here. The takeaway is just, this is so well integrated with my remote that you're able to have the self-contained notebook that gives you this interactive Yara rule development experience. So that's the end of the notebook about Yara. There are some additional features here that you're encouraged to explore. But if you have any suggestions on how to use these features to build more complex or useful functionality, then definitely share it on Discord or an X or Blue Sky or something. This is just something that we have been exploring lately. It's not meant to be this is the way to do things.